It's Kate BYP with a video to explain to you how, thank you, Kitty, how the HP, I was going to show it to you, apparently I'm not now, how the HP 8660 makes frequencies. These units are around, these are not ham radio toys. This is scientific laboratory, and let's just get right down to it, military equipment. This generator is able to resolve one cycle up to about a couple gigahertz. Be aware of information online, especially even the forums. Most of the folk that know something about this kind of stuff are dead and gone or don't care, not online. And much of the information and much of these forums are run by people with ham licenses that think they know it all, and they don't know anything. I caught one of them telling somebody that he could change the detector diode in a power meter with just any old diode. So the information you get on these forums is pretty much worth that. So don't go there. The critical thing to note is it a problem of frequency generation in this unit, or is it a problem with the frequency counter being used? Such a high-end unit implies we need a similarly high-end counter. This 8660 was made in the 1980s. It's ancient equipment. Only a fool would expect to buy one, plug it in, and get stability and accuracy. 40 years of edge card connectors getting flaky contacts and a bunch of bad filter capacitors on distributed power supplies, and you ain't going to get it. I restored this A660 by replacing probably 120 capacitors, cleaned edge card connectors, repaired minor things, few solder joints. And on a modern high-speed 10-place frequency counter, on a 10-second sampling interval, got 8 millihertz stability. Now, if you stop and think about it, a unit that can only generate 1 hertz intervals, that's extraordinary. But let's say this unit's freaking out and it's inaccurate. My unit would show accuracy at 10 megahertz. But if I went to some different frequency, then the output, the display on the counter was a bit erratic, down to ones and tens places. Is that really a problem in a generator, or is that a problem in the counter, or is it noise in either or both? Well, this is a full factory service manual for the A660. It does a very poor job of explaining how this system works. But what you need to see is on figure 812, 8-91, and service sheet 35, output register from the digital control unit DCU on 8162. You can get this manual online. This is not a big variable frequency oscillator. All the stuff in this mainframe does not make the output signal. The output signal is made over here at high frequencies by the frequency extension module, which has a YIG, which is a crystal oscillator. There's a crystal in the YIG. There's a crystal over here in the frequency reference. There are no crystals in between. That output is sent to the RF section, the plug-in section, on the right here, 3.95 to 405 gigahertz, 275 to 395. Those are from the YIG unit. And those are mixed and down converted to the output signal. The purposes for that are filtering and noise and all that crap, harmonics and such. But all this stuff over here does not make the frequency. All this stuff over here makes a digital representation, more or less, of what the frequency was that was keyed into the digital control unit over here. Now, yes, these inputs here, 100 meg, 20, 360 to 450, those are frequency inputs, they're signs. Notice also pre-tune, 10 megahertz, pre-tune 1 jig, 100 megahertz. Those are digital inputs. So the frequencies generated are analog and the controls are digital. But the interesting thing about the control circuits is that there's no place in here that says I'm going to make 550 megahertz, and you won't find 550 megahertz in here anyplace. This is not an RF oscillator. What it does is it assembles 550 megahertz from pieces, and those pieces are represented by these dividers with the 1 hertz 4 lines, 10 hertz 4 lines in the N3, N2 100 hertz 1 kilohertz 10 kilohertz, and 100 kc 1 megahertz with RF outputs in the neighborhood of 20 megahertz. That assembles from a digital code an analog phase locked loop output of 20.000001 to 30 megahertz. And notice that defines the resolution of this unit. Above that are inputs: 100 megahertz reference master oscillator, 500, 20 megahertz, and all that is derived from the 10 megahertz reference oscillator, the Crystal 11. So the reference, this A4 assembly generates a 100 megahertz master clock, 500 megahertz derived, divided by 5, 20 megahertz derived, divided by 2, 10 megahertz derived. And then for the digital control unit, 2 megahertz, which is divided down to 1 megahertz for the system clock, and 400 kilohertz, 100, and 100 kilohertz to drive these tuning loops. Now they're not, don't think of them necessarily as analog tuning, it's digital tuning. Yes, they drive voltage controlled oscillator outputs, but the control's digital. The output frequency is assembled from a 10 wide BCD output register in a digital control unit. Before the DCU, they used thumb wheel switches, represented by a bank of 10 thumb wheel switches. And by the way, if a DCU pukes, just put in a thumb wheel or make a thumb wheel unit. But that 10 BCD output is a representation of frequency. What the digital control unit does is give enunciation, verification of what's keyed in, which is kind of useless. And what the thumb wheel unit cannot do, it gives frequency sweep, the ramp output. The 1 to 10 BCD are for frequency. The higher order digits, up to 13, are to implement the sweep functions. And then over here is the remote input. Forget about that. This 10 BCD output only changes for the digits that need to change. In other words, the 10 megahertz signal has a leading 1 and all zeros. To make 10 megahertz and 1 hertz, 10.000001, the output register does not reload the entire width of that BCD word or words. It only changes the least significant bit or least significant digit. So the 10 megahertz doesn't change, the 1 hertz does. And the manual says that's so that for each frequency change, it's not unlocking and goofing up all these phase-locked networks and all these PLLs, because if that happens, then the entire unit becomes unstable and generates noise and harmonics and all kinds of trash. So what that means is if we're chasing a problem of it's an accurate output except for the kilohertz, then we look at this BCD output. Where is the 1 kilohertz digit in that BCD output? Well, if we look at the N1, 2, and 3 boards, we see we would not look at the N3 unit because that is 1 hertz to 10 hertz. We'd look at the N2, And it's perfectly possible for this thing to be absolutely stable at 10 megahertz, but they're not at 10 megahertz and 1 kilohertz. It might be stable at 10 megahertz and 100 hertz, but not 1 kc. So the 1 kilohertz influence, if you will, comes into the N2 board. There are also pre-tune inputs, and that goes to voltage controlled oscillators, 20.01, 21, 19.8, 29.79, etc., to make that range of 20.000001 to 30 megahertz. So if we're looking at a fault at a certain frequency, try other frequencies that don't use that digit. So in other words, if there's an error at the 1 kilohertz, we don't say that 1 kilohertz or 1.01 kilohertz is necessarily a problem of the N3 board. The 1 kilohertz in this VCO on the M2 might be unstable. The big picture is that it's asking for disaster to just jump in this unit and start going through the alignment and testing procedures, which start up here and go through every circuit. Use some common sense when approaching this, because you can do more damage and cause more misalignment by going through the entire procedure willy-nilly if you're looking for a specific problem. And this is how to narrow it down if that's what the problem is. I saw some stability problems in my unit. It would indicate exactly 10 megahertz to 10 places on my Rigol counter. But if I went between 10 and 100 megahertz, there read some instability on the lower order places. Some instabilities down to a few cycles or a few tens of cycles. When I put the counter on a 10-second period, it read perfectly. That suggests noise. And in a unit like this that might have 6,000 connections, solder joints, wires, edge card connections, any one of these can cause a mess. There was a comment on the HP Agilent forum about someone that had an instability, and they identified which card it was, took the card out, looked around, put it back in, the instability was gone, and attributed that to the edge card connector. Not likely. It's probably a bad solder joint on the board. But this is why I hammer on recapping. Always recap old equipment, because that process also exercises those edge card connectors and gives a chance to look for bad solder joints. Now note, this is a 10-bit BCD output, but there are not 10 bits used in here. The other 2 bits are used for the gigahertz, the very highest frequencies, over here in the extension module, but not in the RF section. See, there are no digital inputs to the RF section. So if you got a missing signal, weak signal, what I found was that this vernier, that level setting pot, was extremely noisy. So I took them apart and cleaned them. But understand that, that a frequency counter can see noise as a frequency error. It can see a change in amplitude as a frequency error. If we consider frequency of a sine wave, for example, is the gradient, the tangent line to that sine signal at some sampling point. A higher frequency has a steeper tangent line. If the amplitude suddenly changes, then that redefines that tangent, and it looks like some other frequency. The description of how the BCD output works is here on the output register assembly. But to boil it down, assume the RF output's been 1.60 megahertz and changed to 1.1. The output binary 1 of digit 6 of U8 goes high and others remain unchanged. So the 100 kilohertz output is on U8 and it's digit 6. We would not go trying to troubleshoot other digits. And realize that these digital outputs, this is not a strobed This is not a pulsed output. These are DC outputs. The output register latches and it doesn't refresh. It holds until something's changed. So a voltmeter is sufficient and necessary for chasing problems to first go through and verify that the BCD output agrees with what's keyed in. And then, since it's so easy, use a scope to look for noise on those lines and unplug these cards and plug them back in. And that's how to isolate the digital control unit. So that's how to go about finding errors and frequencies. Don't go tearing into the reference oscillators. Yes, they must be correct. The service procedure for working on these is unplug, plug in coaxial connectors. The quick connect RF connectors are SMB, Sierra Mike Bravo. In this unit, they're not threaded, they're plug-in. So that requires special cables if you want to unplug a cable and adapt it and plug it into your scope. What I'd recommend, and I haven't tried it, but I'd recommend going back old school, use a radio receiver and wrap 5 or 10 turns of fine wire around the coax with a signal you want to measure and connect it to a broadband radio receiver that will tune in 100 megahertz. You can't hear a 0 beat, so adjust the receiver to a couple hundred hertz higher than what that frequency should be, and use a frequency counter on the audio output of the receiver to indicate the audio frequency, which is the difference between the 100 megahertz signal being received and the 100 megahertz plus 500 cycles that the receiver's turned to. And that should be able to pick up on a receiver that can sense a fraction of a microvolt. You should be able to pick up signal off that cable without disconnecting things. That's a kind of a clunky procedure, but it eliminates having to go disconnecting a bunch of cables with the risk of damaging something, breaking a cable. Never work on something like this without an anti-static workstation. A mat and a grounding strap aren't necessarily enough. So there's the overview. That information I just gave you is in the manual, but they do a very poor job of explaining it. They explain it from the viewpoint of someone with tribal knowledge that already knows this. But we, 40 some years later, may not know it. So there it is. Don't go diving into something like this unless you know what you're looking for. You can cause more damage than you fix. Okay, BYP did it.